So one of the nice things about Bolt is that you have snapshot isolation, which means that when you're running a transaction, and usually this means you're talking about a read transaction, you're seeing the state of the database that existed as you started your transaction. So no matter what happens in the meanwhile, you still see the original things. And that's, once again, one of those things that is really easy to reason about. You see a frozen state of the database for the duration of your transaction. And this comes back to the earlier thing about, like, you really don't want to leak open transactions. Why? Because they freeze a snapshot of your database permanently as long as they exist, which means you can never free those pages of data, which means you're using more and more disk. So it's not a fun thing to do, and the view and update functions are really useful for kind of guarding against that problem. Okay, so snapshot isolation. This is a demo of like proving that it is a snapshot isolation. We have two channels here, reading and written, that work as signaling mechanisms back and forth. We have a go routine, which means it started in the background. This runs in the background. That does a put operation just like earlier. I define a function and then I call db update with that function. Here, I wait to receive from the channel reading, so I know that somebody is reading. Somebody has done something to this channel. So I am inside a write transaction, but I wait for a reader to exist, just to cause that situation where I'm changing the database while somebody is reading it. And then I display a message, I open that bucket and write to the key X. I put in the value updated. And at the end I say X now has a new value, and I close the written channel to signal that I have written to X now. Okay, so on the other side of this picture, we have a read-only transaction that closes the reading channel as a signal that I am now reading. I am in a read-only transaction already. The transaction is open, and then waits for the write to happen. So the other function, most of it runs in between these two lines. And I'm using these as synchronization mechanisms. So now it says back to reading, and then I read the value of X and display it. So if I do this, it says reading, and waits for the written channel. It says updating, X now has a new value. We come back to reading, and we read the value. It's still initial. So the database snapshot did not change from underneath us, even though a transaction completed while we were here. And that makes it kind of easy to think about what's going on. And if you go through like SQL database literature, you will find that different SQL servers have different behavior, and it's all really confusing. This is a single, easy model, and it's actually really nice to reason about. And it's like well documented, this is what it is. Okay, so buckets. A lot of the key value stores that exist have this concept of buckets, which is a way of grouping your keys. Say you install a bunch of servers that have some sort of a distributed database. It's kind of limiting if all your keys are in a single namespace. So buckets are a way of namespacing it. So you might have one bucket that is user accounts, another bucket that is messages, another bucket that is, let's say, clicks, something like that. So you just group things. So one of the nice things we did with Bolt is that I asked them, Ben did it. There's nested buckets. So a bucket can contain buckets. And for example, I'm myself using that to group things and like have them in logical groupings that make sense to me as the application programmer. So that's kind of what it looks like. So this will create 3 buckets, one inside the other. And you can see that the first one returns bucket here, is assigned to this bucket variable. And then the next one is a method call on bucket and is assigned to sub. And the third one is a method call on sub and is assigned to deep. So we dig in deeper. And similarly on the consuming side, instead of create bucket, we do bucket, and they don't have a separate error return because there are no errors apart from the bucket doesn't exist. So you can get a nil on every bit. One of the things that was here as a little note is that you really should not store these values anywhere because their lifetime is within that transaction. If you store them and the transaction exits, the database may change from underneath you, bad things can happen. It's like, don't do that. There's some protection against it, but it will lead to bugs, it will lead to corruption, crash, or an error message. If you're lucky, the third one. Okay, and this is what the API will probably switch to. So instead of doing the 3 separate calls, you can just pass them all as bar args, variable arguments. So however many you want to descend into, you can do in a single call. And the real benefit here is that you don't repeat the error checking. So that's what it'll probably look like in like a week or two. So Bolt is developing really fast. It's like literally it happens every day. Which also means that the API isn't all that stable, but it's kind of easy to work around. The changes are intuitive. I've never had a problem. I've lived through like 20 different API changes already. Okay, so the data types. On the top level, you have a database, which is what you got from an open. Then you have the transaction, that is the thing passed to view and update functions. And within that transaction, you can have buckets that we just saw, and you can also have a thing called cursor, which we saw in the prefix and range queries. And you can get a cursor that is top level, or you can get a cursor that is looking within a bucket. And a cursor will see the sub-buckets and keys on that level. And the way you can tell the difference is that buckets have a value of nil, whereas keys have a value of a byte slice. So it's like, if it has data assigned to it, then it's a key. If not, it's a bucket. So this is kind of the structure of Bolt. And it really, hopefully, comes across as simple because that's what it is. Okay, so Bolt is really fast. And it comes with a simple benchmark that I ran this on my desktop machine. And this is a clutch version that isn't anywhere in the repo yet, but it's basically, these are sequential, and these are, the latter two are randomized. And of these two, the one without the temp driven clause is using an Intel SSD, and this is hitting a temp file system. So you can see that the temp file system is a little bit faster, but that's the same results in a more readable format. So we can see that a cursor scan, as in going through the table in order, goes through 32 million items a second, and it doesn't matter whether it's an SSD or a temp file system. An SSD doesn't really change. So what this kind of means here, the fact that the left and the right column are the same for the read operations, means that Bolt is really good about using your memory as a cache, and that's part of the design of it. That's kind of the reason why it is the way it is to have this actually be true. And for write operations, sequential 160,000 operations a second, and if they are in random order but in a single big transaction always, they are 120,000 operations a second. Now, the big transaction means that Bolt gets to sort them before it does anything about them, so it kind of takes away a little bit of that random order there, but that's still kind of interesting. And now if you switch from an SSD to the temp file system, you can see that it gets like 1.3 to 1.8 times faster, which to me means that there is not much reason to buy faster I/O devices. It's getting close to that limit already right now. I mean, in the future, this ratio may get better, and then you benefit from like a Fusion I/O or whatever. But right now, a good SSD will get you pretty high up.
This is for working so that fits in RAM.
Yeah. Bolt is honestly best for that sort of stuff.
Okay.
I'll talk more about the implementation of it. This is not necessarily the best possible benchmark, so like, caveat, do your own research. This is what comes with Bolt. I also wrote a benchmark myself, which is a little bit different. I am doing a torture test. So the transaction size is 1. It will still fit in memory, but it's hitting the disk a lot on write operations. Every single transaction gets committed to disk. So, and I'm comparing it against the LMDB thing as used from Go. Go adds a little bit of an overhead. So what we see here is, once again, for the reads, the top 4 rows, the left and the right column are kind of close to each other. So it is pretty much as good on reads as it ever will be. Like, it is literally using your memory, not your disk, for the reads, which is kind of what every data store should be, but they're not always good. Okay, and what we can also see is that comparing these two numbers, LMDB as used from Go, at this version, this is running the tip of Go, as in what will be 1.3. LMDB is twice the speed. Go used to be a lot slower, so they were a little bit more neck and neck, but right now it's going this way. But still, something that's a young project compared to a thing written in C that has had a couple of years of tuning to it, I think half the speed is pretty good to begin with. Like, this is where we start. So that's kind of nice. Now, at the bottom, if you compare the write speeds, you can see that switching from an SSD to a temp file system makes it go faster, like 2.5 times faster for Bolt. And this is kind of funny. I don't know what's going on here, but LMDB is seeing up to 400 times the speed. And those question marks out there as in, I'm not sure if I should trust this or not. That's kind of funny. But anyway. And once again, for the actual SSD operations, we're seeing about half the speed of LMDB. And LMDB is considered like lightning fast. So that's really good, honestly. But what this makes it sound like is that Bolt is about half of the speed, but when all the I/O bottlenecks are removed, there's some overheads that are bigger than with LMDB. But still, going pretty fast. It's hard to have the rest of the application keep up with that. So how does this happen? Why is it that fast? What tricks does it pull off? Well, there's a thing called zero copy. So what it actually does is that the database file is M-mapped read-only. And all the data accesses are literally memory accesses. And the kernel is in charge of managing the cache of, like, where do we keep it in memory? How much of it is in memory? When do we load it into memory? All of that is the kernel's domain, and it's just accessing memory. So essentially it has a B tree stored in memory that it just accesses on a get. And that's what makes it that fast. And this is why it's like so clearly aimed at read-heavy workloads, because it just finds the right location in the memory and reads it. And when it hands you back a byte slice, as in here's the key, here's the value, those byte slices actually point to the M-mapped memory. So it doesn't even need to allocate memory for those operations. Which also means that if you have a larger value, something that's, say, bigger than 4 kilobytes, if you were to send that out to the network, it might not even have to go to the CPU's memory, ever. It might go directly from the RAM chips to the network card. So there's all kinds of funny things there. Now, the flip side, as I said earlier, don't hold these things, don't hold on to them longer than the transaction is alive. If you are handed a byte slice of the database, and the transaction returns, and you still hold on to that, and the database changes from underneath you, well, there will be something else now at that memory location. So don't hold on to the byte slices for longer than the duration of the transaction. So the memory map thing is read-only. So what we have here is a get of a key, and we just try to mutate it a little. Let's just change the first byte. Just a little, not much. So what will happen is that it will crash, and it will crash with a, so what that says is, it's a, I think there's supposed to be one extra line of error message there. Huh. Maybe it's, there we go. Scroll bars. So it says unexpected fault address blah blah blah. So the memory management unit is forbidding your write to this location. So if you see this sort of a crash, you kind of know what bug you have. Okay, So the downside of zero copy is that the bulk database pages are what kernel thinks they are. So it cannot compress like a chunk of the database by itself. Now you can compress the values. You can put multiple of your keys and values together and compress them. You can build things on top of Bolt. But Bolt itself can't really compress your things because it needs to hand back the byte slice. And that byte slice has to be what the kernel thinks it is. But you can do kernel level compression. So you can compress the whole thing on your file system if you have a file system that supports that, or if you have a block device that supports that. So for example, ButterFS, you just do the ch-adder plus C. And if you happen to be using one of those file systems like ButterFS that does a lot of fancy tricks, another thing that is beneficial is the plus capital C, which means no copy and write, which is just a little bit more efficient and less protected, but Bolt takes care of its own protection. So it could leave some junk in the file, but Bolt is careful to work in a way where the junk is harmless. Okay, so you can get compression, and it actually usually, even for like random files, if you turn on ButterFS compression, it will go faster on the average. So Bolt is a low-level thing. This is not like your SQL engine. This is not on that level at all. It's a building block that can do interesting things. So, for example, transaction batching, combining multiple writes to a single disk write. That belongs in your application, not in Bolt. Write-ahead log, something that, for example, was in the LSM, the log-structured merge tree, the LMDB design was that it would pile up the writes first and hold them in memory and write them to a journal. And then when the journal gets big enough, flushes them to the permanent location. All of that stuff, it belongs in your application. And there's a really simple reason why. You can get more benefit out of it by integrating it tightly with your application. Now, in the traditional world of SQL, the application was the SQL server, and it integrated tightly into this stuff. But now it's like you can kind of skip the SQL level if you want, but then all of this becomes your responsibility. Or you need to write or find a library on top of Bolt that does it for you, which probably will happen at some point. But it's always a question of like, what are the trade-offs? Okay, so Bolt is a key value store. It's pure Go. It's a library, not a service. The file is meant to be used by a single process at a time. It's an ordered key value store using a B+ tree or a B Snowman tree. You have a single writing transaction at a time. The reading transactions have snapshot isolation. You have buckets to organize your data. You can nest them. Bolt is pretty darn fast, and it uses fancy zero copy tricks to make that possible. And it's intended to be kind of like a low-level building block of do something useful on top of it. I'm using it directly in an application and enjoying it, but I'm weird that way. So that was it. Bolt is on GitHub at BoltDb/Bolt. These slides are on my website, eagain.net. And Basil is an interesting project that I've been working on, which you might want to check out, and I will talk about that later. Thank you. Questions? Anything?
So there's always someone talking about they're going to write a Redis clone in Go. Is this a reasonable building block to use to do that, or is the single process thing make it?
You could probably. I think Redis is kind of partitioned by the primary key kind of easily. So there might be gimmicks you can pull off, but even just the fact that you take multiple Redis operations, multiple Redis commands, and batch them into a single Bolt transaction would probably get you kind of far. Everything that arrives within 3 milliseconds of each other until at most a maximum of 100 commands get batched into a single transaction. You would do that sort of a trick. If I was writing a Redis clone, which I've been kind of pondering about several times, I just don't have a personal use for it. What I would probably do is build distribution into it from day one. But each node in itself could use a Bolt database, and those nodes could coordinate with something like Raft. And you could absolutely make that happen.
are the use cases that you're using this database for?
So Bazel is a distributed file system, the kind of thing where instead of distributed meaning it's a cluster of servers, distributed meaning it's my desktop machine and my laptop machine and a cloud server. I'm using Bazel for the sort of local storage of the file system metadata. So the file content is not in Bazel, but things like there exists a directory which you have this access to that contains these files that are these inodes. That stuff is in Bolt. And my options were pretty much something like SQLite or something, a key value store. And Bolt just seems flexible enough that it was my best match. I started off using LeviGo, which is a LevelDB wrapper for Go. The API is a little bit painful. I was a little bit worried about the fact that most file system workloads are read heavy. So it wasn't a natural match for that necessarily. And then I discovered LMDB, or LMDB was open source at that point, and I switched to the MDB SQL wrapper for it. I used that for a while. I really enjoyed the idea that my database content is mapped into memory, so there's like less caching overhead, less that sort of the usual problem is that you have the kernel caching the blocks of disk that were read by the database, and then the database caches the rows of data. So now you have the same bytes twice in memory. And like that's why big SQL servers try to do like what they call direct I/O to avoid the kernel caching. But that's not realistic for something that runs on this little laptop here, and that's just not the way it's done in that scale. To do direct I/O and that sort of stuff well, you kind of need to dedicate the machine to that role. So I was like happy to find this setup where there is no double caching. So I really enjoyed the design, and when Bolt came out, I was like, it's the exact same thing with a less painful API.
Did you benchmark LevelDB versus?
It's exactly what you expect. LevelDB writes faster, reads slower. It really is exactly that. So the nice thing about Bolt is also that by its nature, it never needs compaction as such.